Today we will demonstrate Michelson interferometer. Using the Michelson interferometer, what we can do in the laboratory. So, basically aim of this experiment are the following: determine the wavelength of the laser source by observing the fringe obtained in the Michelson interferometer. Determine the base angle of a Fresnel's biprism by introducing it in one of the arm of the Michelson interferometer. Okay. So, let us discuss the Michelson interferometers, what it is. So, we have a source, say laser source. Now, from laser source, light is coming and we are using a convex lens. So, laser source generally it gives parallel rays, its divergence is very small. So, almost parallel rays we get. So, we use for this experiment we need basically extended source. Okay. So, if we use normal, not laser source, normal source, generally we use a glass plate and that glass plate basically act as the extended source. This light falls on this glass plate. So, glass plate is taken as the extended source. So, in this case we are using laser to defocus. To make the extended source we use lens. So, lens is not put at the laser is not put at the focal point of this lens. If we put focal point of this lens, then these parallel rays will meet at the focal point, okay, on the other side. So, now it is either greater than this focal length or less than the focal length, then it will diverge, okay. So, that means we are making extended source using this laser. So, here purpose is different than generally we use laser for making the parallel rays. Here parallel rays, from parallel rays to we are diverging the light to make the extended source. Now, this source, extended source, from this extended source or this divergence light basically falling on a half silvered glass plate or beam splitter. We tell it is a beam splitter, and it's splitted into two. One part is reflected and another part is refracted through this glass plate. So, there are two mirrors in perpendicular direction, mirror M1 and mirror M2. So, this light diffracted refracted light. So, this since it is very thin, so there is no much divergence. So, say it is going the straight, okay, just like transmission, it is a transmit through this, okay. So, it is going and falling on this mirror, then it will reflect back from this mirror, it will fall on the mirror perpendicularly and it will reflect back. If it is at 45 degree, then this reflected ray again it is reflected from this glass plate and come down, okay, it is come down. And another part of this incident ray is the here from this place is the reflected, Again when it is 45 degree, so it will be perpendicular to the incident light. Okay. So, it is, so this ray, refracted ray, it is falling on the another mirror M2 perpendicularly. Okay. So, from this mirror again it will reflect back and it will pass through this glass plate and come down. So, here in this region basically we are getting two refracted rays, reflected rays, one from the mirror 1 M1 and another from the mirror M2, and these two are from the basically from same source. One ray is falling here, so it's called amplitude, division of amplitude. One part of this ray is going this way, another part of this ray is reflected this way, going this way. Okay. So, amplitude, division of amplitude, and then these two are traveling this path and coming in this direction, and these two reflected rays, these two rays will interfere and form the interference fringe. Okay. So, this is the mechanism for interference between two coherent source. So, now the path difference between these two rays which interfere. So, starting from here, one is going and coming back from here downwards, another is going here, coming back and downwards. So, this path is same for this for the two rays which are interfering. So, here it is travelling 2D1 path and here it is travelling twice 2D2 path. Okay. So, path difference will be 2D1 minus 2D2. Okay. So, if D1 minus D2, if it is D, so path difference will be 2D. Now, this 2D, it's here we are considering this light it's falling perpendicularly on this mirror, it is at 45 degree. Okay. So, if we consider another rays which is coming in this direction, dotted line, if this makes angle theta, then for this ray, so it's a basically it will form the central fringe. Okay, at center. Now, this dotted line, so they will come at different angle, Okay. So, they will form fringe, other fringe. Okay. So, here basically angle of inclination will change and we will get different order of fringe. So, two important things, one is if thickness is same, then fringe we get because of the variation of angle of inclination, and if thickness varies, then we get fringe for a particular inclination. Okay. So, in this case thickness is constant. So, that is basically D1 minus D2, okay, that will depend on the position of this mirror. If we keep fixed that one for a particular D, we will get different order of fringe because of different angle, okay, angle of inclination. So, in general it is not 2D, path difference is not 2D, this 2D cos theta. So, 2D cos theta, that is the path difference. Now, 2D cos theta equal to m lambda, that is the condition for bright fringe, that is the condition for bright fringe. Okay. So, we will get this type of fringe pattern. Now, here these circular fringes are formed for particular d and different theta. Okay. So, for central one theta is 0, theta is 0. So, it is 2D. So, now from here you can see 2D equal to m lambda. Okay. So, this is the maximum value because cos theta varies from 0 to 1. So, for theta equal to 0, so this side is the maximum value, okay, and the fringe you will get at the center. So, order of the fringe at the center is maximum, that means m will be maximum. So, if this the order is m, so next one will be m minus 1, next m minus 2, m minus 3. So, when you are going outside from the center, so you are getting the fringe of lower order. Okay. And another case may happen that if we look at the center fringe, okay, it is the mth order. Now, or for any particular circle, it's whatever the order. Now, that is for a particular theta, that circle or that fringe is for a particular order and for a particular m. Okay. So, then that is fixed. Now, if you vary d, if you shift the one of the mirror, so basically you are varying d. So, when you will vary d, what will happen? The order of this say central one, it was m, now order of the central one will increase or decrease depending on the value of the d. Okay. If d increases, you are shifting the mirror this side. Okay. So, m will increase, m will increase. So, what does it mean? So, at the center, so as if this fringe, you will feel that fringe are generating and collapsing to increase the order of the central fringe at the center, as if this more rings are collapsed into the center. If you decrease this d, so m will decrease. Then what will happen? So, to reduce the value order of the center one, it was m. Now, you will feel that these rings are generating from the rings are going out from the center, it is going outside. So, you will feel that fins are appearing. Okay. So, if you just very slowly, so if it is bright one, so if this shifting is lambda by 2, okay. So, since here 2d is there, so if d, the shifting is lambda by 2, okay. So, then it will be this 2d will be lambda, 2d will be lambda. I think that I don't need to consider. So, 2d actually it was for central fringe, it was m lambda. Now, if I so 2d, now d, if I increase by lambda by 2, so d will be basically d plus lambda by 2, d plus lambda by 2 means 2d plus lambda by 2 means So, actually 2D, sorry, I should write. So, 2D for central fringe. Now, if I D increase by lambda by 2, D increase by lambda by 2, so then what will happen? This order M will change. So, this will be some different order. So, this if say M1 lambda, okay. So, this condition you will get 2D equal to, so that is new D. So, this you will get to this, it is basically your actually M lambda minus lambda, okay. So, that is why if you change by lambda by 2 this D, then you are getting basically next order M minus 1 into lambda, okay. So, increasing the distance D for central one, basically you are, if increasing the D, so order of the central one should increase. So, that is new D value, okay. So, this new D value, and if you consider that, if you consider that this for D value, yeah, that is true. For original D value, if it is, it will be M minus 1 lambda, M minus 1 into lambda. Now, if you increase by lambda by 2, then it is going, it becoming M lambda, okay. So, 1 will increase. So, for changing D by lambda by 2, you will get collapsing or appearing of the fringe at the center. So, if you count, so starting from bright, so you are changing. So, for lambda by 4 change, you will get the dark one. So, for lambda by 2, you will get the again bright one, okay. So, basically what is happening, so you are counting the number of fringe collapsing or appearing, okay, changing the distance D, So, if you can note down that distance D and how many are appearing or collapsing, if we can count, then from there basically you can find out the lambda value, okay. So here I told that this path difference is equal to 2D cos theta. So, from here it is not very clear how it is 2D cos theta. It is 2D, so that is clear from this when theta equal to 0. For other theta, how it is 2D cos theta, it is not clear. So, to understand that one, you have to, you have to see this diagram. So, that is basically what happens. So, you have extended source as we are using lens, convex lens to diverge the parallel rays. So, this say extended source. So, 3 points I have taken, S in middle and this then S1, S2, right. So, this is the, so this mirror M1 and this is mirror M2. Now, this is the glass plate, okay. Now, observer, when this is the screen, means observer is seeing the, will be able to see the image of the source, image of the mirror through this glass plate, okay. So, that means it is because of reflection from the glass plate, right. So, So, this glass plate here, so I have just extended, now if you see from here, so where you will see the image of this one of source. So, image, it depends on the perpendicular distance of, see, this from this is the same mirror like mirror. So, if this is the point, so corresponding image you will see just back side at the same distance. So, perpendicular, if you draw perpendicular and take the same distance in back side. So, for this S2, this will be the image position, for this S, this will be the image position, for S1, this will be the image position. So, if you connect it as if observer here, it will see the source, not here, it will see the source here. Okay. Now, similarly for this mirror, this observer will see mirror basically here. Okay. Image of this mirror observer will see here. Okay. So, this, so now observer what will see? Observer will see this is the source, light are going and these two mirrors are there. There will be, so for this source, from these two mirror, there will be image of the source, right. From M2, the image will be here, this one, right. So, I have, so same way you can find out the image position, just draw the normal and take the same distance in back side, right. So, for this point, so this will be the image from the mirror 2 and this will be the image for the from the mirror 1, right. So, basically this source, image of the source from this mirror will be this one for mirror 2 and this one for mirror 1. So, as if from this single source, we are getting two virtual source. So, these two sources are coherent, okay. Since it is extended source. So, we will take this source from each point, okay, for a particular rays, from this point and from this point, okay, these two are the coherent source and rays from this source is say this one and rays from this source say this one. So, they are coming at a particular angle of theta, they will be parallel, Now, these two rays will interfere. Okay. Now, what is the path difference between these two rays? So, if you take normal from this point to on this, so this will be the extra path on this rays, right. So, if this is theta, so this extra path will be cos theta, right. Now, if this mirror distance is d, M1 and M2, this mirror distance is d, not this distance now here, these two mirror M1, M2, if it is d, so this image from this mirror you know that it's become 2D, it will be 2D because the distance from here to here whatever, so you will get this and now distance from here to here and this image of that one again it's this. So, it's that whatever this d once it is counted, so distance this plus this d and then for image again this also this d extra d will come plus this whatever the distance from the mirror 2. Okay. So, that is why this image distance will be double whatever the distance of the mirror. So, if this is d, mirror distance between M1 and M2 in this diagram. So, it will be image distance, it will be 2D. So, this from this picture, as if now we have two coherent source. Now, from two coherent source, if light falls this way, okay, from these two sources they are coming just downwards. So, from center of this, if we consider from the center, so it's a downwards, okay. So, as if we will get, so this is the normal, this is the normal, okay. So, we will get the center fringe, and for any other rays, so one I have considered this from these two sources, these two rays, okay. So, they are parallel and they will interfere. Actually, one should use the laser, one should use the lens, and that lens will converge this parallel rays to a point, okay. So, here there basically we will get the fringe for this rays, and these rays are basically coming at angle theta, okay. Now, for a particular theta, what will happen? So, this angle is basically with respect to the center, taking that as axis. So, you will get a cone, over a cone. So, angle will be theta, and over a cone. So, angle will be same, and if you put your skin like this, okay, so you will get the same path difference on this circle, okay, because 2D sin theta, 2D cos theta. So, D is constant, and for a particular theta, cos theta also constant, okay. So, we will get same path difference over on a circle, okay. For next different angle, so you will get another circle. So, you will get basically many concentric circle for different angle, okay. So, that is why on the skin we are basically getting many concentric circle, and this order of the center one is the maximum, So, here that is what I told this. So, 2D will be m lambda. So, m is maximum. So, when D will change, the m will increase or decrease depending on D is increasing or decreasing. So, that is required to basically collapse or appearing of the fins. To get that fillings, we will see the appearing or collapsing of the fringe when we will change the D, right. We will change the D. So, that is for a particular order, particular fringe. So, we will consider the central fringe where the order is the maximum, okay. So, if we count the collapsing or appearing the fringe, and corresponding the displacement of the D, then basically we can calculate, we can 2D by m, okay. So, we can calculate lambda, wavelength of the laser light, okay. So, this one experiment we will do. Another experiment we will do, that how to find out the angle of biprism, using the Michelson interferometer, okay. So, to understand that one, so basically in one of the arm, so this is the setup as I showed you. So, one of the in one of the arm we will insert the biprism. So, this is the biprism, we will insert the biprism, right. Now, when we will insert the biprism, what will happen? So, here this optical path, instead of T, when biprism is not there. So, whatever this length is T, Okay. So, when we put biprism, then the optical path will be mu t. Mu is the refractive index of this material of the biprism. So, this optical path will be mu t. Okay. So, because of this presence of biprism, what will happen? The path difference, additional path difference will be introduced in the sun, and so that additional path difference is basically mu t minus t, mu t minus t. So that will be the additional path, and you know this basically, so it will be twice, because uh, 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 that if d path difference in one arm, so because of the reflection twice, okay, so that become 2d. Okay. So here also same way, this path difference will be 2 mu minus 1 into t. Okay. So t is this one. Now here what happens? So whatever the whatever the number of fringes appear or collapse, if it is m, so this 2 mu minus 1 t equal to m lambda. So this m and this earlier m is not same. Here before putting the biprism, whatever the order was there of the central one, now after putting this biprism, so optical path will change of the one arm. Okay. So before putting, if it is M1, after putting the central fringe, if it is order is M2, so due to change of the path difference, that is 2 mu minus 1 t additional path difference, that is, okay. So for that, the change of the order of the central fringe will be M1 minus M2. Okay. So that sort it is M. So that means, so what we will do? So here the advantage is that if we can just translate this biprism along this direction, we can change the thickness t. We can change the thickness t, because this is the thickness, this is the thickness. So thickness, if I push up, then thickness will decrease. If we push down, then t will increase. Okay. So for a particular, what we will do, for a particular position of the biprism, we will note down the reading for the position of this biprism. Okay. And whatever the central fringe is there, it has some order. Now I will translate this one, that means I am changing the t, and due to that this order of the central one will change. Okay. So that I can count. Okay. It is collapsing or appearing, I can count how many are collapsing or appearing. Okay. So I will count for 30, 40, and for that how much translation are required, so that I will be able to note down. Okay. So that basically that change of thickness. Okay. So that change, that translation, actually we will relate, that is that this translation we are telling L, and because of that thickness will change. So how they are related, translation and thickness, how they are related. So to get this one, here you can see, so this is the biprism. So one this part I have shown, other part is there. So we are using this part. So this is the angle of prism, of biprism. Okay. So this angle we want to find out. So if this we are shifting the biprism by this length, then change of thickness will be this T, change of thickness will be the T. So, this for small angle, because this phi is very small. So, small angle we can write that phi equal to tan phi equal to this T by L. So, tan phi equal to phi. So, that is why we have written phi equal to T by L. Okay. So, this T is basically we are translating this biprism by L distance, and for that the change of the central fringe is M. So, that will count by appearing or collapsing of the fringe at the center. Okay. So, that means M experimentally M will know, L also will know, right. So, your phi will be so phi will be T by L. So, from this relation T is m lambda by 2 mu minus 1. So, if I put T here, so m lambda by 2 mu minus 1 into L. Okay. So, experimentally we will find out this m, L and this m. Lambda is known from the previous measurement and mu is supplied, refractive index of this one. So, then we can calculate the angle of biprism. Okay. So, this experiment also we will do. So, experimental data how we will note down. So, that is let us just review that one. So, determination of wavelength. So, two part of this experiment, one is determination of the wavelength of the laser source. Okay. So, there we have to change the distance of the mirror. So, least count of the micrometer screw of the mirror. So, that we have to note down. Then what we will do? So, what is the micrometer position, initial position before starting to change the distance of the one mirror. So, initial reading we have to take. So, main scale reading, circular scale reading and total. So, if say it is A, then we will change the distance, okay, and count the number of fringe collapsing. Okay. So, we can take 30, 40, 50 number of collapsing for a particular slowly we have to change and we have to count that one, and then for a final position say m equal to 30, 40, 30 or 40, okay, or 50 whatever. So, for that is the final position of the micrometer. For that we will take reading if say it is B. So, that D1, so the D basically it's the D is basically distance we are changing B minus A. So, here I am writing D1 because in this micrometer here there is a, if I change by say whatever the reading from micrometer we will get, actual change. So, that is the lever action basically, actual change is 10 times is less. Okay. So, we have to divide it by 10. So, that is the mechanism of the micrometer for changing the distance of the mirror. Okay. So, this company has given this ratio 1:10 ratio or 10:1 ratio. Okay. So, we will get D value. So, lambda equal to 2D by lambda 2D by m, and because we are considering the central one. So, theta is 0. Okay. So, this m we are counting for a particular D value, okay, for shifting of mirror by D. So, we can calculate the wavelength. Okay. So, here basically number of fringes collapsed or appeared. So, that is m. So, this you can at least 3 times you should do. and then you will find out lambda, average lambda you can find out. Okay. So, this is one part of the experiment, and second part of the experiment is to find out the angle of the biprism. So, determination of the base angle of the Fresnel's biprism, right. So, for that basically wavelength of the laser source we have measured earlier, or it is supplied. So, that you note down refractive index of the material of the Fresnel's biprism. So, that is also supplied. So, you have to note down least count of the translational stage. In this case, as I told that we will shift the biprism, translate the biprism, and when we will translate by L, corresponding change of the thickness will be T. So, optical path will change, that is mu minus 1 into T, right. So, your effective path difference will be 2 into mu minus 1 into T, right. So, that L value for determining the L value, we will use this translation stage where this Fresnel's biprism is attached. So, that least count of that translation stage we will note down. Okay. Then we will start experiment. Here number of fringe collapsed or appeared. So, again we are seeing the central fringe theta equal to 0. Okay. So, when we will change the optical path. So, earlier we change the distance of the mirror. In this case, we will change the thickness of the biprism, shifting or translating the biprism. Okay. So, now we are translating slowly and counting how many are collapsed and how many are collapsed or appeared. Okay. So, it depends on whether you are going towards higher thickness or lower thickness. So, we will note down the reading position of the translation stage initial before starting, okay, to translate. So, main scale reading, then circular scale or vernier scale depending on the scale here. So, then total say this is A, and after translating by L and corresponding count will be M. So, that final reading again we will note down. So, difference of these two will give you L translation. So, then this is your formula T equal to, or then we will find out corresponding thickness T, m lambda by 2 mu minus 1. So, all parameters are known. So, m we have counted, and yes, mu and lambda are given. So, we will get T. So, experimentally we have measured L, corresponding T we are calculating. So, now angle of the biprism, base angle, this is base angle of the biprism phi is equal to T by L we can calculate. So, again this you can at least take 3 reading, okay, for different translation and different number of corresponding m, and you find out phi and you take the average of this phi, right. So, after taking all this data, getting the result, you have to calculate the error calculation. One is you are calculating the lambda wavelength. So, which formula you have used? Lambda equal to 2 d by m. So, just we take log lambda equal to log 2 plus log d plus log m. So, 2 and m is counting, there is no possibility of error, okay, it is not instrument, I am counting, okay. So, these two have no, it will not give any error. So, only in instrument is giving this d value. So, delta, so they then take differentiation, delta lambda by lambda equal to delta d by d, delta d by d. So, here I have written 2 delta d by d because these d is basically we are taking difference of 2 reading, that is b minus a. Okay. So, so basically error is delta a delta del plus delta b, and delta A equal to delta B equal to we are considering delta D. So, this is basically least count of the your micrometer or translation stage, whatever scale you are using. Okay. So, that is why it is this is your formula for error calculation. Similarly, phi equal to m lambda by 2 mu minus 1 L. Okay. Take log. So, lambda is supplied, so there will not be error attached with it. Mu is supplied, there will not be error attached with it. M also you are counting, there will be no error attached with it. So, only it will be attached with L. Okay. So, delta phi by phi will be delta L by L. I have written again 2 because this L we are finding out from the difference of the initial position and final position, difference of 2 reading. So, that is why, so it will be double 2 delta L. So, 2 into least count of the translation stage. So, that is the basically one has to put, because least count I know. So, this is the formula you will use for the error calculation to find out the base angle of the biprism. Okay. So, this working principle of this instrument Michelson interferometer and how to take data I tried to explain. If you understand this one, so it is doing experiment will be very easy, and taking data also it is more reliably you can take the data and you will get better result. Okay. So, in next class we will demonstrate the experiment in the lab, how to do experiment and take data. So, in next class I will demonstrate. Thank you.